Good evening, and welcome to Truth Report. I'm Alex Truth, and tonight we're pulling back the curtain on a story that sounds like it belongs in a physics lab but has massive implications for the surveillance infrastructure being built around all of us.
I'm Maya Clarity, and Alex, when I first saw this paper come across our desk, I thought the same thing. Particle physics? But then I started reading the details, and what I found is a blueprint for pushing artificial intelligence decision-making to the absolute edge of sensor networks, making split-second judgments about what data to keep and what to throw away, all on a chip smaller than your fingernail.
We're talking about a new paper published on AR14, reference number 2602.15946, titled On-Chip Probabilistic Inference for Charged Particle Tracking at the Sensor Edge. Now, that's a mouthful, so let me break it down. Researchers have developed a way to embed AI directly into sensor hardware, allowing the sensor itself to decide in real time what information matters and what gets discarded, before the data even leaves the chip.
And here's what caught my attention as an investigative journalist. The technology is being developed for the Large Hadron Collider at CERN, one of the most data-intensive scientific instruments ever built. But the principles they're demonstrating, on-chip inference, probabilistic decision-making at the sensor edge, those don't stay in physics labs. They migrate. They always migrate.
So tonight, we're going deep on this. We're going to explain what this technology actually does, why it matters far beyond particle physics, and who stands to gain when AI-powered filtering is embedded directly into the sensors that increasingly surround us in everyday life. Stay with us. This is Truth Report.
Let's start with the science, because understanding what these researchers actually built is critical to understanding the implications. The Large Hadron Collider, operated by CERN near Geneva, smashes protons together at nearly the speed of light. When those protons collide, they produce showers of charged particles that fly outward through layers of silicon pixel detectors. Those detectors generate enormous amounts of data, spatiotemporal ionization patterns that map where particles went and how much energy they deposited.
And here's the core problem these researchers are tackling. According to the paper, the LHC's detectors generate data at rates so extreme that it is physically impossible to save all of it. We're talking about tens of terabytes per second from a single experiment. So right now, trigger systems make crude, fast decisions about which collision events look interesting enough to record. The vast majority of data, sometimes more than 99%, is simply thrown away in real time.
That's the key phrase, Alex. Thrown away in real time. The current trigger systems use relatively simple logic. They're fast but they're blunt instruments. What this new research proposes is fundamentally different. They've implemented probabilistic inference, a form of AI reasoning under uncertainty, directly on the sensor chip itself. Instead of sending raw data upstream to be filtered by a separate trigger system, the sensor makes its own intelligent judgment about what it's seeing.
And the technical achievement here is genuinely impressive. According to the paper, they're using what are called probabilistic graphical models implemented in custom silicon, ASICs or FPGAs, that sit right at the sensor layer. These models can estimate the probability that a particular pattern of pixel hits corresponds to a genuine particle track versus noise or background. The chip essentially asks itself, is this real? Is this interesting? And makes that call in nanoseconds.
The researchers frame this as a solution to the bandwidth bottleneck. If your sensor can intelligently filter data before it ever hits the readout chain, you dramatically reduce the data volume that needs to be transmitted, stored, and processed. For the LHC, this means potentially capturing rare physics events that current trigger systems miss because the existing filters are too crude. That's a legitimate scientific advancement.
And I want to be clear about that. The physics application is genuinely important. The LHC is searching for particles and phenomena that could reshape our understanding of fundamental physics. Better filtering at the sensor edge could help physicists detect subtle signals that current systems discard. The researchers are solving a real scientific problem with an elegant engineering approach.
But here's where we pivot from science reporting to investigative journalism, Alex, because this paper isn't just a physics result. It's a proof of concept for a design philosophy that has enormous implications outside the laboratory. The paper explicitly discusses the broader applicability of edge inference, pushing AI decision-making to the sensor layer in any system facing extreme constraints on bandwidth, latency, and power.
Let's be very specific about what that means. Today, most AI-enabled surveillance systems work on a centralized model. Cameras, microphones, and sensors capture data and send it to central servers where algorithms process it. That architecture has natural bottlenecks and, frankly, natural limitations that serve as accidental privacy protections. The sheer volume of data creates a kind of buffer zone. Not everything can be processed in real time. Storage is finite. Bandwidth is limited.
What this research demonstrates is the technical pathway to eliminating those bottlenecks entirely. Imagine a surveillance camera that doesn't just record video and send it somewhere for analysis. Instead, the sensor chip inside that camera runs its own probabilistic inference in real time, deciding at the pixel level what constitutes a person of interest, an anomalous behavior, a target. The filtering happens before the data even becomes a coherent image. The chip itself is making judgments.
And the power efficiency angle is critical here. One of the major constraints on deploying smart sensors everywhere is energy consumption. Running neural networks or complex inference models requires significant power, which limits where you can place intelligent sensors. The approach demonstrated in this paper, probabilistic graphical models implemented in custom low-power silicon, directly addresses that constraint. It makes edge inference viable in places where current AI chips cannot operate.
Think about what that enables. Smart dust, the long-theorized concept of tiny, ubiquitous sensors scattered through environments, has always been limited by power and processing constraints. Wearable biometric monitors that make instant health or identity judgments. Traffic sensors embedded in roadways that classify and track individual vehicles at the hardware level. Acoustic sensors that distinguish specific voices or sounds on chip. Every one of these applications becomes more feasible when you can do intelligent inference at the sensor edge with minimal power.
Now, I want to address something directly. The researchers who wrote this paper are physicists and engineers solving a legitimate scientific problem. I am not suggesting they developed this technology with surveillance applications in mind. That's not how technology transfer works. What happens, historically and consistently, is that capabilities developed for one purpose migrate to other domains, often driven by commercial interests in government procurement programs.
And the historical record on this is unambiguous. The Internet was a defense research project. GPS was a military navigation system. Facial recognition emerged from academic computer vision research. In every case, technologies developed for specific, often benign purposes were adapted and deployed in ways their original creators never intended and sometimes actively opposed. The question is not whether edge inference will migrate from particle physics to surveillance. The question is how fast and who controls the migration.
Let's talk about who benefits from this technology pathway. First, the defense and intelligence community. The U.S. Department of Defense has been explicitly pursuing what it calls sensor-to-shooter decision chains, where data from sensors is processed and acted upon with minimal human intervention and minimal latency. Edge inference is a critical enabling technology for that vision. If your sensor can make targeting judgments on chip, you've collapsed the entire kill chain into the sensor itself.
The defense applications extend to signals intelligence as well. The NSA and its partner agencies in the Five Eyes Alliance have long faced the problem of data volume. When you're intercepting communications at scale, the bottleneck isn't collection, it's processing. On-chip inference at the sensor edge would allow intercept equipment to make real-time judgments about which communications to capture and which to discard, a capability that fundamentally changes the economics of mass surveillance.
On the commercial side, the company's position to benefit read like a who's who of the surveillance industrial complex. Firms like Palantir, which builds data integration platforms for intelligence agencies and law enforcement. Sensor manufacturers like FLIR Systems and Axis Communications. Chip designers like NVIDIA, which is already pushing AI to the edge with its Jetson platform, and Qualcomm, whose Snapdragon processors increasingly include AI inference capabilities.
And let's not forget the Chinese technology ecosystem, ArXiv. Companies like Hikvision and Dahua, which together manufacture a significant share of the world's surveillance cameras, have been aggressively pursuing edge AI capabilities. The Chinese government's social credit system and its surveillance apparatus in Xinjiang represent perhaps the most advanced deployment of AI-enabled monitoring in human history. Technology that makes edge inference more efficient and lower power directly enhances those systems.
Here's what concerns me most from an investigative standpoint. When AI filtering happens at the sensor edge, it becomes fundamentally less auditable. In a centralized system, you can in principle examine what data was collected, how it was processed, and what decisions were made. There's a data trail. When the sensor itself is making probabilistic judgments about what to keep and what to discard, the discarded information is gone. There is no record that it ever existed.
That's a profound point, and it connects to something the paper itself discusses, the concept of information loss. The researchers are explicit that on-chip inference involves irreversible data reduction. In the physics context, that means potentially losing rare particle interactions. In a surveillance context, it means the system's biases and errors become invisible. If an edge AI sensor decides a particular person isn't a threat and discards the data, there's no way to go back and review that judgment. The evidence of the error is destroyed by the act of making it.
And we know from extensive research on algorithmic bias that AI systems consistently perform worse on marginalized populations. Facial recognition has higher error rates for darker-skinned individuals. Predictive policing algorithms reflect and amplify existing patterns of discriminatory enforcement. When those biased judgments are made at the sensor edge, in hardware, the bias becomes literally baked into the silicon. It's not a software update away from being fixed. It's a fundamental architectural decision.
Let me bring in another dimension here. The paper discusses implementing probabilistic graphical models, which means the system reasons about uncertainty. It doesn't just classify, it assigns probabilities. In a physics experiment, that's rigorous and valuable. But consider what probabilistic classification means in a law enforcement context. A sensor that assigns a 70% probability that someone is carrying a weapon. An acoustic monitor that gives an 85% probability that a sound was a gunshot. These probabilistic judgments, made in milliseconds at the hardware level, could trigger automated responses.
We've already seen the consequences of automated probabilistic systems in law enforcement. ShotSpotter, the acoustic gunshot detection system deployed in dozens of American cities, has been repeatedly shown to generate false positives that send police to locations where no shots were fired, disproportionately in Black and Latino neighborhoods. Now imagine that system's inference engine running not on a central server but on the microphone itself, with even less transparency and even fewer opportunities for human review.
And here's the legal dimension that should alarm everyone. Fourth Amendment jurisprudence in the United States has traditionally distinguished between the collection of data and the analysis of data. Courts have sometimes held that collecting information isn't a search, but analyzing it is. When inference happens on-chip at the sensor edge, that distinction collapses. The sensor is simultaneously collecting and analyzing. The constitutional framework we rely on for privacy protection simply doesn't contemplate this architecture.
The European framework under GDPR and the more recent EU AI Act attempts to regulate high-risk AI systems, including those used in law enforcement and public spaces. But those regulations assume a model where AI processing is identifiable, auditable, and separable from data collection. Edge inference challenges every one of those assumptions. If the AI is embedded in the sensor hardware, running proprietary probabilistic models in custom silicon, how do you audit it? How do you even know it's there?
This brings us to what I think is the most critical question raised by this research, and it's a question about power and control. Alex, who decides what the sensor pays attention to? In the LHC context, physicists define the trigger criteria based on their theoretical models of what particles they're looking for. The edge inference system then implements those criteria at the hardware level. But in a surveillance context, who defines the criteria? Who decides what counts as suspicious, anomalous, or threatening?
And that decision, which is fundamentally a political and social decision about what deserves attention and what can be safely ignored, gets encoded into hardware. It gets translated from a policy choice into a circuit design. It moves from the realm of democratic debate into the realm of engineering specifications. The people affected by those judgments, the communities being surveilled, have no input into and no visibility into how those criteria are defined.
We've seen this pattern repeatedly with surveillance technology. The initial deployment is justified by a compelling use case: terrorism prevention, child safety, public health. But once the infrastructure exists, its use inevitably expands. License plate readers deployed to find stolen cars are used to track immigration activists. Cell site simulators developed for counterterrorism are used in routine drug investigations. COVID contact tracing infrastructure is repurposed for law enforcement. Mission creep isn't a bug in surveillance systems. It's a feature.
Now, let me be fair to the researchers here. The paper from AR14 is a genuine contribution to both physics instrumentation and computer engineering. The technical achievement of implementing efficient probabilistic inference in low-power custom hardware is significant and has many beneficial applications. Medical devices that can make faster diagnostic judgments. Environmental sensors that can detect pollution events in real time. Industrial systems that can identify equipment failures before they cause accidents. These are real benefits.
Absolutely. And the particle physics application itself represents the best of what this technology can do, enabling scientific discovery that expands human knowledge. The researchers should be credited for pushing the boundaries of what's possible in on-chip inference. But as investigative journalists, our job isn't just to celebrate technical achievements. It's to trace the pathways through which those achievements reshape power dynamics in society.
And when we trace that pathway for edge inference, the pattern is concerning. We're looking at a technology that makes surveillance cheaper, more efficient, less power-hungry, and fundamentally less auditable. A technology that pushes decision-making authority into hardware where it becomes invisible and unchallengeable. A technology that collapses the distinction between data collection and data analysis, undermining the legal frameworks designed to protect civil liberties.
The defense establishment has already signaled its interest. DARPA, the Defense Advanced Research Projects Agency, has multiple active programs focused on edge computing and sensor fusion. The intelligence community's venture capital arm, In-Q-Tel, has invested in edge AI companies. The direction of travel is clear, and it's toward a world where the sensors themselves are making the judgments that currently require human analysts.
So let's pull all of this together and talk about what it means for the average person going about their daily life. Right now, when you walk past a surveillance camera, that camera is mostly a dumb sensor. It captures an image and sends it somewhere. The intelligence, such as it is, resides in central systems. That architecture, for all its problems, maintains a separation between observation and judgment. What this research points toward is the collapse of that separation.
In the world being built, and it is being built right now in labs and chip design houses around the world, the camera isn't just watching you. It's judging you. It's running probabilistic inference on your appearance, your gait, your behavior, your associations, and it's making those judgments in hardware, in real time, with no record of the judgments it makes and no mechanism for you to challenge them. The sensor becomes the judge.
And because these judgments happen at the edge, on the chip itself, the data that doesn't meet the filter criteria simply vanishes. If the system decides you're not interesting, there's no record it ever looked at you. If it decides you're interesting, you may never know what triggered that judgment. The probabilistic nature of the inference means the system operates in a permanent fog of uncertainty, making consequential decisions based on likelihood rather than certainty, but presenting those decisions as definitive outputs.
This is why we cover stories like this on Truth Report, Alex. Not because a physics paper is inherently threatening, but because the technology pathway it illuminates leads directly to questions about power, accountability, and the kind of society we want to live in. Edge inference is coming. The question is whether it comes with democratic oversight, transparency requirements, and meaningful protections for civil liberties, or whether it arrives silently, embedded in the infrastructure around us, making invisible judgments that shape our lives.
And right now, the policy conversation is not keeping pace with the technology. Legislators are still debating facial recognition bans while the technology is evolving past centralized facial recognition entirely. The regulatory frameworks being proposed assume architectures that are already being superseded. We're fighting the last war while the next one is being designed in silicon.
So what needs to happen? First, transparency requirements need to be extended to edge devices. If a sensor is running inference, the public has a right to know what models are being used, what criteria they implement, and what data is being discarded. Second, audit mechanisms need to be designed into edge inference systems from the beginning, not bolted on after deployment. Third, there need to be hard legal limits on what judgments can be made at the sensor edge, particularly in public spaces.
And fourth, and this is perhaps the most important point, the public needs to be part of this conversation. The decisions about what our sensors pay attention to and what they ignore are decisions about social priorities and values. They cannot be left to engineers and procurement officers alone. When a community decides to deploy smart sensors in its public spaces, the people who live in that community should have a say in what those sensors are programmed to look for.
The researchers at CERN and their collaborators have given us a remarkable piece of engineering. On-chip probabilistic inference for particle tracking is a genuine breakthrough that will advance fundamental physics. But as we've seen time and again, breakthroughs don't stay in the lab. They escape into the world, and they reshape it in ways their creators never imagined.
That's the story we'll keep following here at Truth Report. The migration of edge inference from physics laboratories to the surveillance infrastructure that increasingly mediates our relationship with public space, with law enforcement, with government power. Because the most consequential technologies aren't the ones that make headlines. They're the ones that disappear into the background, into the chips, into the sensors, into the infrastructure, making judgments we never see about lives we're trying to live.
Before we sign off, let me leave our audience with one thought from the paper itself. The researchers described their system as deciding which information to save for further analysis. In a physics experiment, that's a technical optimization. In a surveillance system, that's a sentence that should send a chill through every free society. Who decides what's worth saving? Who decides what's worth analyzing? And who's accountable when those decisions are wrong?
These are the questions that keep us going here at Truth Report. The questions that don't have easy answers but demand that we keep asking them. Because the alternative, a world where invisible algorithms and invisible chips make invisible judgments about our lives, that's not a world anyone chose. It's a world that was built while no one was paying attention.
And paying attention is exactly what we intend to keep doing. If you found tonight's reporting valuable, share it with someone who needs to hear it. Talk about these issues with your community, your representatives, your school boards, anyone making decisions about censor technology in your public spaces.
For Truth Report, I'm Alex Truth.
And I'm Maya Clarity. Stay informed. Stay vigilant. And most importantly, stay free. We'll see you next time.
Good night, everyone.